Thank you. So this is joint work with Clement, Canonne, Shoham, Letzter, and Erik Waingarten, who is here. So I will talk about the following problem. It's a property testing problem, but I don't write it this way, I don't formulate it this way. So let's say we have, so let's fix some constant k. Think of k as, let's say, I don't know, 3. And let's say we are given a sequence containing many disjoint copies of increasing subsequences of length k. We will call them 1 up to k patterns. And the goal is to find one such pattern with good constant probability. So for example, here you see 3 disjoint copies of 1 up to 3 patterns, and we want to find one of them. So it doesn't have to be one of the original disjoint copies, it doesn't even have to have all of its entries in these original copies. And okay, so this problem turns out to be connected to many other fundamental algorithmic problems, as we will see soon. But let's try a naive algorithm for this kind of problem. So since our sequence contains many disjoint copies of 1 up to k, if we just uniformly sample each entry of the sequence with probability n to the minus 1 over k, then with good probability, at least one pattern will be fully sampled, so all of its elements will be sampled. But we want some algorithm better than that. This is barely sublinear. Here the query complexity is n to the 1 minus 1 over k. Okay, so let's see why this problem is interesting in the first place. So the simplest case, where k equals 2, is basically corresponds to monotonicity testing. So being monotone, non-increasing, is equivalent to having no 1-2 copies, to having no increasing subsequences of length 2. And being far from monotone, non-increasing, is equivalent to having many disjoint copies of 1 and 2. And in fact, this phenomenon is more general. So Dilworth's theorem about partial orders states that if we don't have 1 up to k copies, then our sequence is decomposable into a small number of non-increasing subsequences. So one way to think about our problem is testing with one-sided error whether our sequence is decomposable into, I don't know, 10 monotone subsequences. And in fact, another way to say the same is through the language of the LAS, longest increasing subsequence. So in this problem, given some sequence, we want to find the subsequence as long as possible where the values are increasing. And I want to stress that all the subsequences that we are looking at are non-consecutive. That we don't need to have the values consecutive. So the property that we are interested in is the problem that we're interested in is testing the property of having LAS length less than k for some constant k. Okay, so let's see some previous results on this problem. So monotonicity testing is quite well investigated, and it's known that both the non-adaptive and the adaptive query complexity of this problem is linear in log n. So non-adaptive, I refer to making the queries in advance, and adaptive algorithms are one where you make the queries one by one and can see the results. And in fact, for any fixed k, there is a polylogarithmic query algorithm for this problem. Running time, I won't talk about running time in this talk, so running time is at most quadratic in the query complexity. And okay, so the query complexity is polylogarithmic in n. There is a bound by Neumann, Rabinovich, Rogender, Pasal, and Zoller that gives log n to the of k squared. And there are also some results for the case where k is large. And when k is large, you don't need property testing assumptions. So for when k is small, you have to have some kind of assumption for this problem to make sense. And actually, one of the state-of-the-art results on this front was presented by Said a few hours ago. OK, so our result is in the setting, again, where k is a constant. And we settle the non-adaptive Fourier complexity of this problem. And the answer turns out to be curious. So we give both an upper and a lower bound. And it turns out that the non-adaptive Fourier complexity is theta of log n to the integral part of log k in base 2 for any fixed k. So I hide the dependence on k here. It's not very good, but well, this is an open question. We will see in the end. OK, so let me start by just briefly saying a few words about the lower bound. So for monotonicity testing, the non-adaptive lower bound goes basically like this. There are log n different types of constructions where the evidence for not being monotone appears at different scales. And it turns out that the number of queries that you need to make is at least asymptotically linear in the number of different types. And well, our lower bound is an iterated version of it. It turns out that, so this is, for example, for k equals 8, you iterate 3 times. It turns out that there are a log cubed number of different profiles, and the number of queries that you need to make is at least linear in that. But for most of the talk, I want to discuss the upper bound. And maybe the one takeaway message that I want to give is that you can choose, OK, so given you can choose your copies in a very simple, greedy way, in a manner that will give you some additional properties that just, in some sense, solve this problem. So just the way we choose our disjoint copies will give us a lot algorithmically. OK, so let's consider the following way to choose our disjoint 1 up to k copies. Let's confine ourselves to k equals 2. So we go left to right. And each time we see an element that is not yet colored, that doesn't yet belong to some copy, we try to match it with the leftmost element available. So this gray one will be matched to the first element that is bigger than it. And the second element will be matched to its neighbor, and so on. So this way we will get, if we are far from 1 to 3, from monotone, we will get many disjoint copies of 1 and 2. And they will satisfy some additional property. So I want to give you a very simple claim. And actually, I'll even give you the proof. And the claim is that if, so let's look at x and x prime in this drawing. If x is before x prime, but y that was matched to x comes after y prime, then the value of y is bigger than the value of y prime. And here's the proof. When we looked at x, when we tried to match it to a copy, y prime was a candidate for that. But we didn't take y prime. So the value of y prime is no bigger than the value of x. On the other hand, y was matched to x, so its value is bigger than the value of x. And so the value of y is bigger than the value of y prime. So that's the full proof. And this very simple claim gives you, it does wonders for the structure of the problem. So let's suppose that some point L lies roughly in the middle of many copies that have different widths, that have different scales. So let's see what this claim gives us. We know that the structure that we will see is something like this. So at the smallest scale, the right side element will have a relatively low value, and then at a larger scale, the right side elements will have a larger value and so on. And now this gives us a way to construct increasing subsequences. Let's see how. So if you sample elements at all possible scales, at all possible widths to the right of this element L, and if by any chance we get to hit elements from k different categories, we know that they will constitute an increasing subsequence of length k. And it turns out, I don't want to go into the quantitative details, but it turns out that you just need, assuming that L satisfies this good condition, you just need a logarithmic number of queries. Okay, but what if not? So our structural characterization says that more or less either we have many values that are like in the middle of copies that were in many different scales, or, okay, so what's the opposite? The opposite is that most of the entries don't have many different scales around them of copies. So we'll call this splittable intervals. So the splittable interval condition says that you can cover a constant fraction of our sequence with intervals where there is only one width that is very popular. So all copies that are in this interval have more or less the same distance between the first element and the second element. Okay, and this kind of reasoning can be iterated. So this settles the case k equals 2. It turns out that if you just try to hit, you take off one queries and hope to hit some green element, and then query elements at all possible scales as compared to this green element, then it will find your red one, and this will constitute a 1-to copy. So in the case k equals 2, we are done. Now when k is bigger than 2, so the growing suffixes condition, the previous condition, actually holds for any fixed k. So you still need to pay just log n queries in order to find an increasing subsequence. And in the other case of splittable intervals, we'll need to iterate our argument. So it looks more or less like this. So let's consider the case k equals 4, and let's assume that most of the copies, so there will be a constant fraction of the copies that have the same, where the big gap between their entries will be between, for example, the second and the third element. So we can iterate this argument, and more or less the structures that we will see look something like this. So in the left part that is dense with 1-2 copies, we will have some, it can be split into intervals that are dense in themselves in 1s and 2s, and same for the right side. And also all the values in the right side are bigger than all the values in the left side. And it turns out that this kind of structure can be exploited to find increasing subsequences with log n to the log k query complexity. Okay, let's see why. So the algorithm is quite simple, actually. You start with query a constant number of elements in hope that you will hit some element of some copy. And now, if you look at the right scale, the scale that more or less covers the purple area around this yellow element, so a constant fraction of the elements at this scale will be purple elements that can serve as 1 entries. And similarly, if you look at the right scale to the right, then the right scale will, so the elements in the red part that are, the blue elements in the red part will actually constitute a constant fraction of the elements in this scale. So we just need to query a constant amount of elements in this scale in order to hit a blue element. But it will be hard for us to hit both a blue element and a gray element that corresponds to this blue one. for this, we will need more iterations of our algorithm. So in each iteration, we query elements at all possible scales around our current queried elements. So in the next iteration of our algorithm, we will hit a 4 entry, and this constructs a 1 up to 4 pattern. Just to give a sense of what's going on behind the scenes, so we are considering non-adaptive algorithms. We can imagine that they do whatever we want. So let's imagine we have a tree. And querying an element in the first place and then querying at all possible scales around it is more or less like, well, it can be described like querying a leaf of this tree and then trying to query all elements in the branch that leads to this leaf. So more or less what's going on is that if you choose the right branch, which for our case is a branch that decomposes the tree into subtrees of size at most k over 2. And so with constant probability, the basic operation of starting with querying some element and then elements at all possible widths around it, we'll query elements along this whole branch. And then all that is left to do is find elements that will fill the rest of the trees, of the subtrees, which are of size at most half of the original tree. And OK, so you need to do log of k rounds in order to cover the whole tree, and each round costs log of n queries multiplicatively. So you need log of n to the log of k queries. OK, so this is basically a rough description of the algorithm and why it gives log n to the log k. Now, for future directions, so this algorithm was non-adaptive. And I guess the first question that one may ask is, what can adaptive algorithms do? And in fact, adaptive algorithms match the query complexity of monotonicity testing. So for adaptive algorithms, you only need some constant that depends on k times log n, which is the query complexity of monotonicity testing over the line. And another direction, so our problem assumes that k is a constant. We assume that we have many disjoint copies of increasing subsequences of length k, and this only makes sense when k is a constant. But in fact, so we are still far from fully understanding how to find, how to approximate the LIS length in sublinear time, or how to test for it efficiently. So I think it's natural to understand what's going on when k is not a constant. And one last question that is a generalization of this one is testing for order patterns. So let's suppose we have many disjoint copies of order patterns of fixed length k. The goal is to find one of them. So for example, the pattern 1, 3, 2 means that the first element should be the smallest, the second should be the largest, and the third should be in the middle in terms of value. So it turns out that unlike the monotone case where you have a the polylog algorithm, in the non-adaptive setting here, you can't do much. Okay? So the query complexity is polynomial in n, and in many cases barely sublinear in n. But for the adaptive case, we know almost nothing. So for patterns of length 3, basically, we know that there is a polylog query adaptive algorithm, but basically that's it. OK, so let me conclude here. Thank you.